turn it in tomorrow. You gonna record?
Yeah.
Hello. Is it recording right now?
Yeah.
Oh, it is? So it just got me saying hello.
Yeah.
All right, gotta put your labs away. Yeah, put them away.
That last one was so straight.
You have done 3 already. How many have you done? 3. Pretty easy to see the bounciness, isn't it, when you plot the points? Okay. All right, chapter 12. This next unit will be 12 and 13 combined, but there's a whole lot in there that we don't have to cover. Chapter 12, we're only going to cover a little bit, and the rest of it is no longer on the AP exam. The part we're leaving out, I'm just going to tell you, it makes me sad because it used to be on the AP exam. The part of chapter 12 we're skipping. It's things like Q equals MC delta T, remember that in chemistry? It's not on the AP physics exam, and it's about heat. And something, how much energy does it take to warm something up? But they've taken that out of the exam. However, temperature and some things about heat you still need to know. So we're going to start out talking about temperature. The definition for the word you probably know is the average, what? Kinetic energy of the particles. That's the definition of temperature. It has to do with how fast the molecules are moving. The kinetic energy, the average kinetic energy of all the particles. But all the molecules in the air in this room are not all moving with the same kinetic energy. Some are moving faster than others, whatever. But there's an average, and that average is the temperature. Yeah. Okay, we will get to an equation that takes that definition and quantifies it. We're not going to do that right now. But there is one where if you know the temperature, you can actually calculate the kinetic energy. So that definition will become an equation eventually. But let's keep talking about temperature. There are different scales, aren't there? How many different scales do you know? You know Celsius. What's another one? Kelvin is the SI scale, and then the one we use all the time is Fahrenheit, the one that we use in the United States. You go to almost any other country, they use Celsius. You can just cross the border into Canada, and they use Celsius there. Everywhere else they use Celsius.
Are you bitter that we don't use Celsius?
Am I bitter about that? No. I think we should use Celsius just because it's internationally accepted everywhere except here, just about. And so I think we should, but bitter, why would, I'm not gonna lose any sleep over this. Or,
I would.
That'll be such like a dramatic change though, like if they were like, okay, one day,
Yeah.
like it went over film, like it would be such a.
yeah.
All cars are being kilometers per
I mean, there was a push like back in the 70s and 80s to switch America to the metric system. And they started putting up signs on the highway that said it's, so many miles, but it's also so many kilometers to try to get people used to that. And they started building cars where the speedometer had miles per hour, but it also had kilometers per hour on it. And some still do that. But that push in general just failed because American people didn't want to switch. You grow up learning one thing, you don't want to switch what you know.
I want to switch.
Yeah. Well, in science, we use the SI system, which is pretty much metric, but not in just everyday life in America. We don't do that. Couldn't get them to switch. Anyway, temperature scales. The Fahrenheit scale and the Celsius scale and the Kelvin scale are the 3 that we know most about. There is a 4th one called Rankine. Have you ever heard of Rankine? But I'm not even going to talk about Rankine because nobody uses Rankine. Rankine is like kind of like Celsius and Kelvin are similar.
Are they?
They're similar. If water goes up 1 Celsius degree, you know how many kelvins it went up? 1. See, they're the same. 1 degree here is the same as one of those.
Shoot.
But Fahrenheit's different. If it goes up 1 degree Celsius, it went up more than 1 degree Fahrenheit. See, they're not the same. However, Rankine is like the absolute version of Fahrenheit. If you're curious, I'm just gonna say that. Where 0 Rankine is the same as 0 Kelvin, it's absolute 0 Rankine. But 1 Rankine is the same as one of these. Now, having said that, in case you ever hear it, you'll have heard of it, but it won't ever be on a test, and nobody in the world uses Rankine. All right, so let's talk about these three. You know that water boils at 212 degrees Fahrenheit, right? Water boils here at 100 degrees Celsius, and water boils here at, do you know? Boiling point of water in Kelvin.
Is it?
373 kelvins. Now, if we move down to the freezing point of water, that's 32 in Fahrenheit, isn't it? In Celsius, it's 0, and in Kelvin, that's 273, which is probably the number you remembered, 273. Now, you can stop right here and see, since Celsius is 0 at the same temperature, Kelvin is 273. That's where we got that thing you learned in chemistry 2 years ago, where we learned that Kelvin is Celsius plus 273. That's how you convert from one to the other. And you can see it right here. That's the difference in them. And you can also look and see the difference between boiling and freezing is 100 degrees right here, isn't it? Well, it's also 100 kelvins right here, the difference. So you know that from just that, you know that 1 Kelvin is the same as 1 degree Celsius. If something warms up 10 kelvins, it also warmed up 10 Celsius degrees. And I should also mention here, I'm sure you probably know that we don't use the word degrees with Kelvin. There's no little circle up there. You don't say degrees. They're just called kelvins. This is 273 kelvins, or that's 0 degrees Celsius. All right, so the difference between boiling and freezing is 100. Here, the difference between boiling and freezing is 100. But what's the difference between boiling and freezing over here? It's not 100, is it? It's 180, if you subtract that and that. So, 180 Fahrenheit degrees would be the same as 100 Celsius degrees. Now, if you think about that, 180 is the same as 100. What does that reduce down to? You ever seen 9/5 before? In the equation for converting between these things? There it is. If you invert that, it's 5/9, which is in the equation going the other way. If we carry this further down here, let's go all the way down to 0 kelvins, which is absolute 0. There are no negative numbers in Kelvin. That would be here, that would be negative 273 degrees. So that's absolute 0 in Celsius. Here, I doubt you'll ever be asked. Matter of fact, I don't think you'll ever be asked anything about Fahrenheit on the AP exam. It's just that we use Fahrenheit all the time in our everyday lives. And so you should, I think it's good just in general to have an idea how these things relate. 98.6, which is considered the normal body temperature of a human. That's in Fahrenheit. That's about 38 here. Just if you're ever curious. So you're in Canada and they take your temperature and they say, oh, it's 38. You'll say, oh, good, it's normal. All right. Anyway, yeah, then that's absolute 0 in Fahrenheit. Again, you'll never be asked to know that, but that's what it is in case you ever wonder. One last thing, just to get you thinking about graphs, because you're always needing to be able to think about graphs. If we plotted points of, let's say, Fahrenheit on the y and Celsius on the x, and you got some kind of straight line like this, where, what would the slope of that line be? 9/5, right? That's the relationship between Fahrenheit and Celsius. So the rise over the run would be 9/5, And if you think of y equals mx plus b, which is what you think about when it's a linear relationship like that, the y-axis is Fahrenheit. The m we just said was 9/5. That's the slope. The x is Celsius. And what do you think this y-intercept would be?
Is it 32?
If Celsius is at 0, and that's at 100, then right up here that's at 212.
80?
What's that right there on the y-axis? If Celsius is at 0,
Is it 32?
32.
I said that.
So there is actually, from that graph, is your equation for converting. You probably learned in some science class. It just comes from graphing Fahrenheit versus Celsius, and you come up with that. If you switch the axes, you get the other one. Okay, you're not going to need that though, because we're not ever going to convert between these. The one you'll need is this. You do need to know that. Very little converting on the AP exam, you'll probably know from last year, but that's one thing you often have to convert. They will still give you Celsius and expect you to use Kelvin in the equations. All the equations you're going to learn for temperature, that is the SI scale, and so that's the one you're expected to use. You might even remember in chemistry when we did some temp and temperature things that we always had to convert to kelvins. Like in Pov equals nert, remember that equation?
Yes.
The T in that equation is temperature, it had to be in kelvins. And Pov equals nert is still on the AP exam, we'll get to that. Not in this chapter, but eventually. Okay, so I didn't put that Fahrenheit Celsius equation up because you need to know it for the exam or my test, you don't need to know it. But just to show you how graphs, so many things can just come from graphs. If you just graph the stuff and use it to write an equation, it's a real equation. That's where just about all equations come from. They're derived from graphing data. All right. Now, the next thing you need to know, we have time for at least one more thing. Let me hold on. See if there's anything else besides what I think is next. We did the temperature scales, thermometers. We don't really have to talk about that. We do need to talk about linear expansion. If you heat something, it expands. If you heat something, it expands. Here is a metal rod, and it has a certain length. And then you heat it, and it gets longer. All right, everybody knows that when you heat things, they expand. That's something you learned in elementary school. In this chapter, you need to know how much did it expand. What do you think if I heat it and it grows longer? Okay, let's just say, okay, that was a little bit longer than that because it expanded, because I've heated it here. What are some of the things that matter in terms of delta L? That's the change in length. That's the expansion. How much did it expand? What matters? What makes a difference in how much it's going to get longer? The what? Just what the material is made of itself, which in density is part of that. There is a constant which is represented by the Greek letter alpha.
Aw.
Yeah.
How?
Alpha.
Can't they use another alphabet?
Alpha. I didn't make this up. This was made up by someone else. This is called the coefficient. Does coefficient have two F's in it?
Probably.
The coefficient of linear expansion. Linear means we're just talking about how much longer the rod gets, or anything, how much longer it gets. Expansion. And this constant, the coefficient of linear expansion, simply depends on what the material is. Like lead would have a certain number, and concrete would have a certain number, and iron would have a number, and so forth. There's a chart in your book in chapter 12, we don't need to turn there right now, But when you start doing homework, or even when you start taking notes and reading, you'll see that chart. And it just lists a whole bunch of different substances and tells you what their alpha is. Okay, so that's one of the things that matters. What's it made of? What's another thing that would matter? That's one of the things that makes a difference. What's another thing that would make it expand more or less? Something else that makes a difference.
The temperature?
Yeah, how much you heat it up. The change in temperature, that's how much. If it started out at 20 degrees Celsius and you warmed it up to 40, it's going to expand. But if you warm it up to 80, it's going to expand more, isn't it?
Probably.
So that's another variable. The change in temperature. That's what that is. Delta T.
That's supposed to be period, not temperature. They need to get creative with their.
The change in temperature. Yeah, well, capital T. Capital T is also for temperature, just like it was for period. It still stands for period, also the time it takes something to swing back and forth, for example, but in this chapter is temperature, capital T. Lowercase t is still time, so capital T is temperature. And there's one more thing that makes a difference you might be less likely to think of, but it's pretty obvious once you think about it, and that's the original length. The longer it was to start with, the more it's going to expand. If it's really short to start with, it'll just expand a little. If it's already pretty long and you heat the whole thing, it's going to expand more. So the original length is another variable. So delta L becomes alpha LO delta T. There's the equation. You just put the variables in there and you multiply them together. And that tells you how much it expands. We will stop here today, but we'll come back to this tomorrow and we'll look at some examples of why this is an important thing. Engineers who build things always have to think about how this material is going to expand in the summer and contract in the winter, and how can I build it so it won't crumble when it's doing that. See, so this becomes a big deal when you're building something. All right, we're stopping here today. Your only homework is to finish the lab. That's supposed to do tomorrow.
That equation looks so like physics-y. Like if you didn't know anything, it's just like all symbols, and nobody knows what it means unless you're in physics.
Yeah.